Hi, and welcome to our egg drop project. Today we're going to be showing you the ins and outs of this device we created in order to shield our egg from being obliterated once it hit the ground. The first thing we did was put our egg in a box that had a bunch of assorted balloons in it to provide buoyancy and the ability for our egg not to have too much pressure once the collision with the ground occurs. The second precaution we took involved taping our balloons onto the lid of the box. We made sure to include these balloons as shock absorbers in order to prevent our egg from cracking due to Newton's third law, which states that for every action there's an equal and opposite reaction, which would cause our egg to break if our egg reached a terminal velocity that caused it to have a harsher collision once it hit the ground. Our list of materials includes balloons, duct tape, straws, a box, hot glue, and a clasp. Another aspect of our project that has not been formally introduced yet is its title. We decided to name our project the Sea Turtle Killer, which is quite a morbid name, yet quite accurate as well. One of the best models we found to build our project by included the use of plastic straws, which has been quite the hot topic lately as far as environmental issues are concerned. So we just wanted to let out a formal apology to all the sea turtles in this world, and we promise we'll be using reusable straws from now on. One of the reasons we chose said straws is because of their strength, yet their light mass. We didn't want our project to be made out of something that was quite hefty, as that would increase the mass and therefore increase the force of which it hits the ground, which would cause our egg to break. We arranged these straws in a geometric pattern that was highly influenced by triangles, because triangles are one of the strongest shapes, and we wanted to include that to make sure that our project had the soundest design. When discussing how Newton's laws affect our project, one would start naturally with Newton's first law, which states that an object in motion stays in motion. This law is rather important because it basically declares the well-known fact that inertia is something that affects all objects while falling or free falling. Our object, the egg itself, its force is determined by the object's mass and the acceleration of that said object. Our egg, you can't really control the mass of the egg, as we were all given our own eggs, but we could control the acceleration through the effectiveness of our egg drop design, which is why we tried to include as much air resistance as possible by putting paper on the outsides of our project so that air would be trapped inside and provide more air resistance so that the terminal velocity would be reached sooner. This was evident in our project due to the fact that our mechanism's mass was quite slim, therefore the acceleration of our object was slim as well. It was quite slow compared to other projects. The third law states that any action is countered by another action of an equal magnitude, but in the opposite direction. This explains the collision portion of our project, as once our project hit the ground, the collision between our object and the ground was enough to slightly crack the egg, but not enough to create a damage that was quite evident. A design concern we were worried about was whether or not our project was sturdy enough to protect our egg. As it turns out, it actually was. Our project, there was a complication due to the fact that the extremely windy weather caused our project to sort of drift in the air due to the fact that we had quite a bit of air resistance built into our project through paper being placed on the tops and sides of our vehicle. A concern we had was that since it was made out of straws, it wouldn't be able to withstand the collision and protect the egg. However, these concerns were proved to be not valid, considering the fact that our egg was protected during the collision, even though it was from a very high distance. Our acceleration is constant, as our object was in free fall, therefore the only force acting upon it was gravity. Therefore, the acceleration would not change. One value we did not calculate due to its complexity was drag. When calculating drag, you have to previously calculate the drag coefficient, CD. which requires you to know different information such as the reference area and the density of your object. Although this would have been a very interesting value to calculate, it wasn't realistic due to our limitations as far as measurements are concerned during drop day. Another value that would have been interesting to calculate was torque way. This is a measure of the ability of a force to rotate an object around an axis. This would have been interesting for our project, considering our project, once we dropped it, it seemed to twirl about in the air before it hit the ground, and it would be interesting to see how many times it actually did a full rotation. If I was to find a way to calculate these values, I think a little more time would be necessary during the actual reaction, and we would have to have some more technology that was able to capture certain values, such as the exact time it took for our project to make a complete rotation. After looking at our calculations, it's important to note the certain values that we sort of overlooked or paid less attention to when calculating. The main value that we sort of tended to assume information about was air resistance. We sort of didn't account for the complete amount of air resistance we encountered during our project due to the fact that it was extremely windy the day we dropped it, which was one of the problems in our execution. If I was to do this project again, the way I would fix our previous issues with our project would be by accounting for the possibility of having a lot of wind the day of our drop, and I would put less paper on the outside of our project so that our project would fall directly towards the ground and there would be less of a chance of our project rotating and accidentally falling on its weaker end, which is what happened during our execution. I would also alter our design so that both ends would have a larger surface area. That way, even if it did land on the opposite end to which we anticipated, it would still have less force hitting the egg directly once it fell, which would allow us to have less force transferred to the egg, and possibly help us with a better end result. Thank you so much for watching. We hope you enjoyed, and we hope that now you have more information on how to execute such a fascinating experiment. Goodbye!